Welcome, this is the AP Physics video lecture. This is going to be covering centripetal force, now with friction. I want you to review the different ways we saw centripetal force. We saw it both vertically and horizontally. The first scenario is when we spin an object in a circular path, and here it was in a circle up and down. And we saw the centripetal force here is supplied by the tension and gravity. So summation of the force centripetal is equal to force tension minus force gravity, depending on its location. When it's bottom, it's a minus, and when it's on top, it's an addition. We also saw it when it doesn't have tension, so there's no string here, like a Ferris wheel goes up and down on a circular path around the Ferris wheel, which is a circular object. Here we saw that the centripetal force, Fc, is made up of two things, the normal force and the force gravity, and depending on its location. So on bottom, we saw force normal minus Fg, and on top, force normal is going to be still going up against force gravity. Okay, that's on top of the circle. Now we saw that it can be completely horizontal, like when we spin the object in a horizontal circular path. We saw that the force centripetal is equal to the tension force. So here the centripetal force that is acting on this object or supplying the centripetal force is the force tension. Notice none of these are on a surface or mention friction in any way. But you have to remember how we set up these. So a typical scenario that you're going to see is that a mass is moving in a circular path, but this time it's on a frictionless surface. So the free body diagram, first of all, there are two views. There's the side view and there is the bird eye view. From the side, you see the dot, force gravity is pointing down, force normal is going up. Same length, because they have to be the same length because it stays on the flat of the horizontal circle. It doesn't move up or down. And we know that it continues its path because the force tension, which is along the string, is pointing towards the center of the circle. If you look at it from the bird's eye view, which is on top looking down, we see that there is an arrow only pointing towards the center, and it is the force of tension. Now we could set up the force equations here. There's the horizontal direction and the vertical direction. I'm going to do the vertical direction first. We notice that there is no movement up or down. It's completely flat. So the summation of the force in the y direction equals to 0. The two forces there are your normal force minus your force gravity. The forces in the y direction are in equilibrium, and if we add Fg to both sides, you get the normal force is equal to the gravitational force. Now we can look at the horizontal direction. The horizontal direction, we see from the bird's eye point of view, is supplied by the force of tension. So here, the summation of the centripetal force is equal to the force of tension. The centripetal force here is in the x direction. Make the substitution, it becomes mv squared over r is equal to the force of tension. Now, the questions could ask you for what is the tension force, what is the velocity, what is the radius, and so on and so on. But this is the typical setup of an object in a horizontal path. And this is frictionless. This is another situation, but this time we introduce a hanging mass. So a puck of mass m is on a frictionless table and is attached to a hanging mass m by a cord through a hole in the table. Find the speed in which m must move in order for big mass m to stay at rest. So it's the same thing here, but now there is a mass hanging. Set up the same thing. So the free body diagram on A, which is the puck free body diagram, and you want us to look at the hanging masses free body diagram. So from the puck's point of view, it's like the last problem that we did. Force gravity is pointing down, which is just mg here, little m. Force normal going up, and force tension, which is going towards the center of the circle. From the hanging mass, it is Force gravity is making it go down, and its equation would be big M, because that's the mass, big M times G. And what is going up is the tension force. Now you want to look at the forces in either direction. Let's do the vertical direction first. The vertical direction is when the object is in equilibrium. So the only thing that you have is the summation of the forces in the y direction is equal to 0. The only thing that you have is the tension minus Fg. Where am I getting that? This. That's where I'm getting it. Okay. So if I solve for it, I notice that the tension force is equal to force gravity, or in this case, the force of gravity on the big object, big M and G. Now we could look at the horizontal direction. We saw that the centripetal force here is in the x direction, the horizontal direction. So summation of the force centripetal is equal to the force tension. Make the substitution. You should already seen this before. The question arises is to understand what Ft is, but we know what force of tension is because we got it. Force tension was equal to, right there, big M G. So make that substitution. Now they ask you to solve for V. So we work the algebra. You get V equals to the square root big M over M GR. Okay. One thing that you should notice, why Ft is equal to mg is that, notice that the Ft here is along this path, right? This is Ft, but it curves down. That's Ft. There's also an Ft going up that cancels with it. What's really going down is the force of gravity. So this is like this problem, the Atwood machine one. Oops, sorry. It's like the Atwood machine where you have a mass here, a pulley, and a hanging mass. Okay, we saw here that the tension force here that's around the loop, they're internal forces, so they cancel out. The only thing that is dragging this object down is the force of gravity on the hanging mass. That's essentially what is happening here. It behaves the same way. So this is another way to see that idea of the centripetal force. So at a particular speed here, the mass should stay at rest. If it goes too slow, the mass is going to fall down. And if it goes too fast, the mass is going to get lifted up. Okay? This is a physics 1 question in this section. This section of centripetal force is done a lot with experimental design and argumentation. The first question, you could read it to yourself here, but it asks which quality or qualities must be measured to determine the tangential speed required to keep the system in equilibrium. So it's like the last thing. So I'm just going to grab the equation. And we saw from the equation what you need was M2, M1, and R. G is already known as to be 9 meters per second squared. So you only need the mass on the table, mass hanging, and the radius. That's it. That's all you need to know for the velocity. So, will you ever be asked to derive this? No. But you have to understand the implementation of it. Next, same scenario. This is an experimental of the same situation. There's a mass revolving and a hanging mass here. But here they ask you, what do you need to measure to what are the necessary devices needed by the student to collect the necessary data to determine the gravitational field strength of the object of m naught due to Earth's gravitational field. All it's asking for is this equation and solving for velocity, okay, or m. And we know that all we need here is mass. So this is your mass We need the R. So that is your length. So that's where your meter stick is. So this is for your mass. This is your length, your meter stick. All right. That's also the L here as well. Okay, the length of the rope. Sometimes you see that as radius. T is your period. And this is the unit here is second. So this is where you need the timer. So this is for the period. Okay. You do not need the motion detector. The motion detector will tell you the change of X or the change of Y. So the motion detector is used if you want to see like the displacement of something. So you don't need the motion detector. Now we're going to introduce friction to it. So there are two scenarios. It could be like before, and they just say on a rough table. More likely, you're going to see this as a car moving around a circular track. And we know that it is on a track, and the track has a coefficient of friction. So let's draw the free body diagram. Here's the car. Force gravity is pointing down. Force normal is going up. Exactly the same. We see that there is a force going towards the center of the circle, which is applying the centripetal the centripetal acceleration, and here it would be force of friction. From the bird's eye point view, looking down, we could see it is only the force of friction that is keeping the object in the circle. So, what is causing the car to not slid out? It's actually the force of friction. The force of friction is actually pointing towards the center of the circle. Okay? 2. Now we could set up the force equations. I'm going to do the vertical one first. We know that the force in the y direction equals to 0. It's the normal force minus force gravity. The forces in the y direction are equilibrium. The car isn't going up or down the track. Okay, it's staying leveled. So the normal force equals to mg. You need to get the normal force here because, again, we are dealing with friction. And remember, friction is mu n. So let me write that for you. Friction is mu n, right? N is the normal force. So now we could see that the horizontal direction, and we see that the centripetal force here, the summation of the centripetal force is equal to the force of static friction because the object's already moving. So the centripetal force here is in the x direction. So make the substitution. mv squared over r is what Fc is, and we know that force of static friction is mu n, but we know that n is equal to mg. That's how I get mu mg here. The masses cancel out, and we see that v squared divided by r will equal to mu g. This is a typical question, but sometimes it asks us for its velocity. So, like before, the car is moving it on a circular path on a rough track, and we saw how we got here. Now they're going to ask for a particular speed. So, like before, we can solve for v. Mass cancels out. You multiply r to the other side, and you square root it. And you get v equals to the square root of mu gr. This is the maximum speed the car can travel before it flies off the track, because here the centripetal force is equal to the frictional force. But there's this case where velocity is greater than that and when velocity is less than that. What do those two mean? When velocity is greater than the square root of mu gr, that is when the speed goes so fast that it flies off the track. There isn't enough force gravity to, there isn't enough force friction to keep the object on the track, to keep it in its circular path, so it's going to go off it. Now, what happens if velocity is less? Well, the speed is so low that there is no chance that the car will fly off the track. So these are the three scenarios that you're going to see how V interacts when the car goes around its circular path. Let's look at an argumentation question here. because this section is asked either experimental design or an argumentation. So here, Stephanie is a Formula One driver. Her average speed over the famous Monte Carlo Grand Prix curve, this is a famous curve here, if you look at the pictures, is 50 kilometers per hour. When the track is dry, mu is equal to 0.8. She needs to know if she can speed up or slow down when the track is wet. Mu equals to 0.4. Argue what she needs to do and by how much. This is the curve here. Figure 1 shows the dry track and figure 2 shows the wet track. Your intuition by looking at the picture should already give you a understanding of its speed around this corner. Notice that the cars are more separated when it's the wet track, right? So think about that. So what do you think is her claim? Students believe she needs to slow down. Here's the evidence. Summation of the force of the centripetal force is the force friction. We saw that in the last example. Plug in the substitution, mass cancels, multiply r to the other side. But now, in this case, I'm only looking at the velocity and the mu because g and r are constant, so I can just ignore it. The difference in the scenario is by a 1/2. How am I getting the 1/2 here? I'm doing the original mu. The final mu was 0.4 and the initial mu was 0.8. So the factor is by 1/2. That's how I got the 1/2 here. Right? So if I do the square root of 1/2, I get the velocity as 0.707. So her new velocity, the new velocity that she needs to have is going to be reduced by a factor of 0.707. Okay? If the mu is half, so it went from 0.8 to 0.4, you half it. So the square root of a half is basically 0.707. So here's the reason. Since the radius, so this is just the math. Remember, the evidence is just the math. You want to start writing the words during the reasoning part. So I write, since the radius and gravitational acceleration is constant, the reason why I write this line is because it justifies why I could ignore GR. Once I ignore GR, that's how I get square root mu. Then I said that mu is proportionally to the square of the velocity. This is what this is describing. So velocity squared. Do you see that right here? Velocity squared is equal to mu. So mu is proportionally to the square of velocity. Make sure you mention that. Next, when mu is reduced by a factor of 1/2, that is what I am mentioning right here. When mu is reduced by a factor of 1/2, the velocity changes by a factor right here of 0.707. Her new speed should be 0.707. So this is the scale factor multiplied by her original speed, which is 50 kilometers per hour. So the fact that the coefficient is halved, the velocity factor is 0.707. So that is her new speed. It is lower because the v here is less than 1. So her speed is dramatically less. So there you go. This is the complete difference. These numbers are actually true, right? I kind of rounded the mu for the dry track. The mu of the dry track is roughly 0.71, but if you round it, I round it to 0.8. And this is actually the speed of the cars during the Grand Prix. So these are real numbers here. Look, it changes dramatically from 50 kilometers per hour to 35 kilometers per hour. Okay, this is the reason why drivers here are taking this curve so much slower, because like what we did before here, if they're not equal, the car will fly off the track. Okay, so here, if velocity is greater than that mu, if this car right here that is on the wet track goes 36 kilometers per hour, it's gonna it's going to slide off. If it stays under 35, okay, it's going to be good. And its maximum speed, which is 35, that's when it will go completely tangential. All right? So, there you go. That's everything that you need to know for the centripetal force, now with friction.